Hello friends, welcome to lecture 6 of digital signal processing. In this lecture, we will study about Fourier transform. Yeah. Without any wait, let's start. As we have seen previously in lecture 4 that every signal can be represented as a scaled sum of many number of sinusoids. Therefore, many sequences can be represented by a Fourier integral of the form okay, where this xn, we can say that it is superposition of infinitesimally small complex sinusoids. Okay. While on the other hand, x e j omega can be written as this. Okay, so this is a complex valued function of omega. Complex valued function of omega, periodic with period 2 pi, and again we can calculate its magnitude response and phase response. So this is actually the Fourier transform of xn. Okay, so Fourier transform is also referred to as Fourier spectrum or simply spectrum. Okay. Now the angle. We can calculate its magnitude response or phase response. The angle is not uniquely specified because this angle, let's call it theta. Theta equals to theta plus 2 pi r, where r is any integer. Okay, so this is not uniquely specified. So, but when we are talking about the principal value, so usually we refer to as the principal value of theta. So that principal value is from minus pi to plus pi. Okay, let's go ahead. Now let's talk about the frequency response of LTI system. Okay, so we have seen in lecture 5 that frequency response can be written like this. And just now we have seen that x of e j omega is written like this. Here k and n are just dummy variables. We can use any. We can use them interchangeably. Like we can use n here or we can use k here, because in summation they will go away. So this implies that frequency response of LTI system is simply the Fourier transform of impulse response. Okay, did you caught it what I said? the frequency response of LTI system, which is h e j omega, is Fourier transform of impulse response. Okay. So yeah, usually if we have to prove that these two operations are inverse of each other, so how would we prove it? So let's do some maths on this. So we know that, I'll just write those equations again. Minus pi to pi x e j omega d omega. We have to prove that these two equations are inverse of each other. So I'll put x e j omega in this equation, minus pi to pi, and instead of n I'll take another variable m, x m e to the minus j omega m to the j omega n d omega, and let's say it is x hat n. Okay, and to prove that, to prove about the inverse Fourier transform, if the infinite sum converges uniformly for all values of omega, then we can actually interchange this summation and the integral. If the infinite sum converges uniformly for all values of omega. Okay, so it will be 1 upon 2 pi summation over m x m integral minus pi to pi e to the j omega n minus m d omega. So this integral is actually equals to sine pi n minus m over pi n minus m. Okay, and I'm just talking about this integral, and this is equals to 1 when n is equals to m, equals to 0 when n is not equals to m. In other words, so basically then the x hat n is equals to summation over m x m delta n minus m. We can write like this also, which is basically nothing but xn. Okay, hence proved that these two operations are inverse of each other. Okay, now let's talk about the condition for existence of Fourier transform. I'll write Fourier transform as ft. So if xn is absolutely summable, then Fourier transform exists. If xn is absolutely summable, then its Fourier transform exists. So what do we mean by this? So again, Fourier transform exists mean it follows this for all values of omega. That means is equals to summation over n x n to the minus j omega. This will be less than equals to if we take the individual summations. Okay, this is magnitude of this is 1. Fine, this is less than infinity. Thus this represents, thus if xn is absolutely summable, or the summation of absolute values of x are bounded by infinity or less than infinity, then the Fourier transform exists. So this also means that a stable sequence is by definition absolutely summable. So that implies that all stable sequences have Fourier transform. Okay, so let's take an example. Let's take xn equals to an exponential multiplied by unit step function. So its Fourier transform as I'll write n equals to 0 to infinity, because this is un here will be this. This is nothing but a into e to the minus j omega to the whole power n. We can write this as minus a e minus j omega if mod of a is less than 1. So this is basically a condition. If we follow this, then the Fourier transform exists. Okay. So some sequences are not absolutely summable but are square summable. Okay. So there are some sequences which are not absolutely summable, but they are square summable. Which means that you follow this. So these can be represented by Fourier transform if we relax the condition of uniform convergence of the infinite sum defining the Fourier transform. Okay, which means something like this, that if we take the Fourier transform over m numbers, which will be from minus m to plus m, the same expression inside a to the minus j omega n, then it will follow that limit m tends to infinity minus pi to pi the square of this 0. So this means that the total energy in the error tends to 0 as m tends to infinity. Okay, so there is a workaround for the signal which are not absolutely summable. Okay, so let's understand this by another example. Let's take xn equals to 1. So this is neither absolutely summable nor square summable. Okay, that's why the Fourier transform converges neither in uniform nor in mean square sense. And its Fourier transform can be written like this. This actually you can verify by taking the inverse of this. Okay, so it is possible and useful to define the Fourier transform of xn to be periodic impulse string. Okay, so here we can see that this is a continuous variable. We all know the Fourier transform of discrete time signal is a continuous function, and this impulse, as this is just a series of impulse of in continuous time or in a continuous variable. So this is infinite height, zero width. That means we have unit area. I mean all properties of a continuous domain impulse. So this is actually consistent with the fact that the Fourier transform for signal like this does not converge. Okay. Okay. Now let's come to the symmetry properties of Fourier transform. So they are very useful in simplifying the solution of problems. That's why we should know them. And before presenting the properties, we will begin with some definitions. So first definition is conjugate symmetric sequence. So they are defined like this. Where this stands for complex number, and conjugate asymmetric they are defined like this. So any sequence can be expressed as sum of conjugate symmetric and conjugate asymmetric sequence. For example, if there is a sequence xn, it can be written like this, where the conjugate symmetric part can be written like this. You can verify here that it actually follows this, and conjugate asymmetric function part can be written as this, which you can verify follows this. Okay, so a real sequence that is conjugate symmetric, a real sequence which is conjugate symmetric is a even sequence, is an even sequence. On the other hand, a real sequence which is conjugate asymmetric is an odd sequence. You can actually verify it from here, from the above equations. This is just to understand the properties. I want to mention them, otherwise verification of them is very easy. Okay. Similarly, a Fourier transform can also be decomposed into sum of conjugate symmetric and conjugate asymmetric functions as like this. Okay, where again the conjugate symmetric part can be written as this, while the conjugate asymmetric part can be written as this. Notice there is a minus sign in these two terms here. Okay. Yeah. So these are the various symmetric properties of Fourier transform. Okay. Fine. So if you look on, let's say, the property number 3 here, where the Fourier transform of a real of xn is the conjugate symmetric part of the xej omega. So let's try to solve it. So real of xn can be written like this. Okay. So taking its Fourier transform, this is simple. X e j omega plus x star e minus j x star of this, which is nothing but the conjugate symmetric of x e j omega. Okay. Yeah. So going over the other properties, similarly the imaginary of the signal, you can find the Fourier transform, the even part, the conjugate symmetric part, conjugate asymmetric part, any real x, and so on, and for the even and odd part. So if you keep these properties handy, it's very easy to solve the complex problems. Actually, these are the use cases of the symmetric properties of Fourier transform. Okay, so now let's take a look on some of the Fourier transform theorems. Okay, so these are some of the Fourier transform theorems. Yeah, so first one is just a linear operation, nothing much complex here. Second, this is a time shift property. So this means that if there is a shift in time domain, that represents there is a phase shift in frequency domain, and vice versa. If there is a frequency shift, there is a phase shift in time domain. This is time reversal. This is differentiation in frequency domain. Yeah, and this is convolution. If you look 6 and 7 together, let's try to understand like this, that if there is a convolution in time domain, there is a multiplication in frequency domain. If there is a multiplication in time domain, there is a convolution in time domain. Okay, the last one, the Parseval's theorem. These actually tells about the energy. Okay, so understand it like this, that energy in time domain and frequency domain are same. If you are taking the Fourier transform, it's not impacting the energy. Okay, these are the Parseval's theorem. Okay, now let's take a look on some of the Fourier transform pairs. Fine. This is an impulse. If time domain there is an impulse, it's all ones in the frequency domain, and vice versa. So you can visualize it like this, that if there is an impulse, or the signal is limited in time domain, it will be unlimited or unlimited in frequency domain. Okay, this we have already verified. This is unit step function. Yeah, so okay, when we calculate the Fourier transform of unit step function, we can see there is a series of impulse trains. So actually this is keep in mind that when we draw unit step function in time domain, there comes discontinuity. So if there is a discontinuity, then that means there has to be some impulse trains or series of impulses in frequency domain. Okay, fine. This is a rectangular function in frequency domain. That means that in time domain it's a sinc, and vice versa. If there is a rectangular in time domain, there will be sinc in frequency domain. Okay, yeah, so let's calculate one of them. Let's calculate the Fourier transform of a rectangular function in time domain. Okay, so that actually looks something like this. Let's say this is our time domain for 0 to m. This is 1. Actually, I've drawn it like a continuous domain function, but let's draw in discrete domain. So for n equals to 0, this is 1. For n equals to 1, this is 1, and so on for till n equals to m. Okay, this is 1. Okay, so let's calculate the Fourier transform. We can calculate it like this is m. Okay, this is just this is a geometric series, so this will be, these are m plus 1 terms. Okay, take e to the minus j omega m plus 1 by 2 common. It will be to the plus j omega m plus 1 by 2 e to the minus j omega m plus 1 by 2 divided by, take e to the minus j omega by 2 common from denominator. It will be e to the j omega by 2 minus e to the minus j omega by 2. Okay, so it will be e to the minus j omega m by 2. This is the phase part. The magnitude part can be written like this. Okay, yeah, so this is the Fourier transform of a rectangular function. Yeah, if you look here, we are talking about this. Okay, fine.